Today, being the National Mathematics Day, this webinar is a very humble attempt to honor the greatest Indian mathematics genius, Srinivasa Ramanujan, who left behind a unique and iconic legacy of unparalleled discoveries in mathematics that strongly impacted the ocean of mathematics geniuses. As I introduce to you our keynote speaker, Professor Tazid Ali, a humble and renowned mathematician from Dibrugarh University, Assam. He has been a professor for the last 8 years at the university in Dibrugarh. He was the former head of the Department of Mathematics and presently Chairperson, Center for Computer Science and Applications. His area of interest is very interesting though, mathematics in genetics and fuzzy sets. Well, dignitaries present here, I present to you the keynote speaker, Professor Tazid Ali. Now before, sir, you begin your lecture, I would request our principal, Professor Gajanan Madiwal, to kindly welcome the keynote speaker, Professor Tazid Ali. Thank you.
Good afternoon, everyone.
Good afternoon.
I think I am audible. I am
Yes,
audible.
Yes.
you're audible.
Yes.
Yeah, all the audience, and I welcome for this special occasion on this day of the mathematics, Professor Tazid Ali from Dibrugarh University, Assam. Sir, we welcome you, and I want to tell that we are from the commerce background, most of us. And this particular webinar is at a national level we organize due to some of the some of the students have not joined, and it's from maybe rural connectivity problems, etc. So we welcome you for this special day on the foundations of mathematics. And before that, I want to tell my experience with this particular special subject, mathematics. Most important subject, but many times our students are not taking much interest in the mathematics when it's made compulsory. Especially when we talk about that, some of the students very much attracted by this particular subject. And Professor, it is my general observation. I made it. Many of us, we don't know the applicability of the mathematics in our real life. And we find it difficult, even our research students also, where to apply, which type of mathematics, etc. Especially, we find it applications of the operational research, etc. And even the simplest maths, such as the matrix, it is used in the logistics. Many times we don't want to use it. Sometimes we calculate logistics moments, etc., in a different manners. This one. And regarding my little bit, I studied astrology, and I found it some astrology something else. But afterwards, I realized that those days also, without looking at the telescope and movement of the what you call the movements of the maybe sun or the all the other planets are calculated by the astronomy, whatever the what you call the Dibrugarh in the Sanskrit is called. Dibrugarh, based on that, we used to calculate. And till today, we are using that. And it's a wonderful maths. You can see that longitude and that whatever the latitudes are there from that particular, what is the visibility area of the eclipse, etc. Calculate the mass. And I can say that, Professor, you have to take a little bit lead in this particular thing. Everything is possible through the mathematics. That is, people are not aware. Even this one, they are not aware that the if you look at the chemistry people are using, the helium, when you see when you liquefied helium gas, the moment is calculated first time through the mathematics only, how it moves and etc. It may be star's death or the stars the birth are also calculated through the mathematics. And what is the lagging in the mathematics is that is the application. We don't know a lot of maths things are related only understood by the scholars like Professor Tazid Ali and people like us, common people. We don't understand many times where we can use it, make use of this particular mathematics in our real life. And for my experience, I have a small contribution I did in this regard is Vedic mathematics. And I studied Vedic mathematics and written a book on the small for the children. And I developed certain things of the digital root methods on that. And I found it that is this mathematical today students somehow they don't want to learn it. This is my observation. And the mathematics is given as option, they leave in. And you find one thing you find those who are interested in the mathematics subject, they come forward and they do the wonder. With interest, they come. And this you might have observed in your university also. The students are coming for the mathematics. If you ask them that, absolutely they don't have any other interest and they come for this particular course to take maths and learn maths and live with the maths. And with this particular small introduction, I welcome you, sir, and also I also thankful for the organizer, Ms. Martin, and he's the professor in a particular our department, mathematics department, and looking after this mathematics department and the students on this particular institution. We have a subject on that particular thing. Thank you, sir. We also welcome on behalf of the college for this particular webinar. Thank you, everyone.
Thank you, sir. Thank you, Principal. Now I request the keynote speaker, Professor Tazid Ali, to go ahead. The floor is all yours.
So very good afternoon to all of you.
Good afternoon.
First, I'd like to thank the organizers of this webinar, the principal of the college, head of Department of Mathematics, Martins, and head of Department of Computer Studies, Dr. K. Desai. So I thank them for inviting me to deliver this talk today. So I'll first share a few slides on Ramanujan, and then I'll go to the main topic of our deliberation, that is the foundation of mathematics.
Yes, sir.
So Srinivasan Ramanujan Iyengar, as you know, born in Tamil Nadu in the place called Erode in 22nd December 1887. So his father was a K. Srinivasa Iyengar and mother was Komala Mal. He was married to S. Janaki in the year 1909. That is, I think he was 22 years by then. When he was very young, between 12 to 13 years, he mastered S.L. Loni's trigonometry. There was a book by Loni, Trigonometry, and at the young age of 12 to 13 years, he mastered the whole book. And at the age of 16, he came across a book by George Kerr called A Synopsis of Elementary Results on Pure and Applied Mathematics. It is a 2-volume encyclopedia containing more than 6,000 results on different branches of mathematics. Now, Ramanujan not only worked out all the theorems in the book, but he derived some new results from the book. In 1903, he passed his matriculation under Madras University and he got a scholarship and joined Government College of Kumbakonam. However, as he was too much interested in mathematics, he neglected other subjects and he failed in all the other subjects, so he lost his scholarship. But he managed to get another scholarship and join a college, Pachayappa College. But here also, same thing happened. He couldn't concentrate on the other subjects and failed. So he couldn't get a degree there. Now, he was actually coming from a very economically weak family. So driven by poverty, he was forced to join as a clerk at the Port Trust Office, Madras, and the salary was just 25 rupees. Okay, so this was Ramanujan.
Yes.
Then his parents, I have told already, K. Srinivasan Iyengar and mother, Komala Tamal. He married as Janaki in 1909. And between 12 to 13 years, he mastered completely the book on trigonometry by Loni. And at the age of 16, he came across a book called The Synopsis of Elementary Results in Pure and Applied Mathematics. It is a 2-volume encyclopedia containing more than 6,000 results on different branches of mathematics. He not only worked out all the theorems in the book, but derived some new results also. And in 1903, he passed his matriculation under Madras University and joined Government College of Kumbakonam with a scholarship. But he couldn't concentrate on other subjects, so he lost his scholarship as he failed in all the subjects other than mathematics. Then he joined another college, Pachayappa, and also managed to get another scholarship. But here also same thing happened. As he failed in all the subjects, he couldn't continue further. He was driven by poverty, so he had to join as a clerk at the Post Trust Office, Madras, at a salary of ₹25 only. Now, Ramanujan's approach to mathematics was unconventional. Most of his results were without proof, and even where proofs are given, they lack mathematical rigor. Now, this basically happened because he was not having any formal training or education in mathematics like we do have nowadays. His work was not appreciated by the Indian mathematicians. He approached many Indian mathematicians, but they couldn't actually understand what he was doing. So one Narayana Iyer, who was then the chief accountant of Port Trust, Madras, he advised Ramanujan to write to some mathematician in England. Ramanujan wrote to some 3 or 4 mathematicians, but they didn't reply except one, and that was G.H. Hardy of Cambridge University. Now, when Hardy saw the results of Ramanujan, he exclaimed, "I have never seen anything like them before. The theorems had to be true because no one had the imagination to invent them." Now, as I told that Ramanujan was unconventional in his approach, so whatever he simply gave the results. He never gave the proofs. So Hardy was not sure whether the results are true, but still he thought that the results are so beautiful that they must be true, because one cannot write those results simply from imagination. Then Hardy invited Ramanujan, and Ramanujan went to England in 1914. There both Ramanujan and Hardy wrote 32 research papers. Then in 1916, Ramanujan received his BA degree. See, when Ramanujan went to England, he was not having any BA degree, but at Cambridge University, he received his BA degree. Then in 1917, he was elected to the Royal Society of London. And in 1918, he was elected as Fellow of Trinity College, and he was the first Indian to be honored so. Now, what happened? One day, out of frustration, Ramanujan attempted to commit suicide by running before a train because he was having some problems. However, he was rescued and hospitalized. And at the hospital, Hardy came to visit. And Hardy said that he came to the hospital by a taxi, and the taxi bear the number 1729. And Hardy said that the number appeared to him to be very dull. But Ramanujan thought for a while and then shouted, No, it is a very interesting number because it is the smallest number that can be expressed as the sum of 2 cubes in 2 different ways. As you can see, 1729 can be expressed as 1 cube plus 12 cube. It can be also expressed as 9 cube plus 10 cube. So it is the smallest such number which can be expressed as the sum of cubes of 2 different ways. And the next number after 1729 is 4140. Now, Ramanujan attributed his mathematical discoveries to divine revelation received from Hindu goddess Namagiri, a consort of lion god Narasimha. Sometimes at midnight, he would wake up and start writing formulas and equations in his notebook. On being asked, he would say that he worked out mathematics inspired by the goddess Namagiri in his dreams, and now jolting down the results. As I told earlier, that Ramanujan simply gave the results. he never gave the proofs. And Ramanujan feels that in his dreams, the goddess used to come and give him the results. And in the morning, he simply writes them down in his notebook. Once he remarked, an equation has no meaning for me unless it expresses a thought of God. For example, he considered the expression 2 to the power minus 1. He said that it stood for primordial God and several divinities. For example, when n is 0, we get 0, the expression denotes 0, and it means nothingness, it denotes nothingness. When n is 1, the expression is 1, that is unity, and it represents infinite God. When n is 2, the expression is 3, value is 3, and it denotes the Trinity. When n is 7, the expression becomes 7, so it represents the subtertiary and so on. Now, Ramanujan even built a theory around 0 and infinity, where 0 represented absolute reality and infinity was the immediate manifestation of that reality. After returning from England, Ramanujan returned from England in 1919. And after returning from England, he developed some new formulas. And after his death, his wife handed all those notes to the Madras University. And from Madras University, it was sent to British mathematician G.N. Watson. And Watson, what he did a lot of research on his results. Because the results were given, no proof were given, so Watson worked on the proof of those results. Now, after Watson's death, these notes were handed over to the library of Trinity College, Cambridge. Now, these notes contain more than 600 formulas developed by Ramanujan. And no proof of this note. P.C. Barnett published several books, wherein they put many formulas of Ramanujan as given in the notebook. The proof requires some of the most sophisticated mathematical tools like complex analysis and Galois theory. As Ramanujan was not familiar with these tools, it appears that he must have obtained his results by some alternative and profound approach. Because this Galois theory and complex analysis were not familiar with Ramanujan, but still Ramanujan could write or find those results. That means there must be some different approach through which Ramanujan got the results. Barnett expressed his opinion on the notebook as, the discovery of this last notebook caused as much stir in the mathematical world as Beethoven's 10th Symphony in the world of classical music. Ramanujan worked on different areas like partition theory, continued fractions, modular equations, Mohr functions, elliptic functions, etc. Now, mathematicians worked and are still working on the generalization, extension, as well as on notes left behind by Ramanujan. And working on these notes, several mathematicians won different prizes. Even one mathematician, the Belgian mathematician P. Deligne, received the Fields Medal. As we know, Fields Medal is equivalent to the Nobel Prize, because in mathematics we don't have Nobel Prize. So Fields Medal is considered to be equivalent to Nobel Prize. And one of the mathematician, P. Deligne, he received the Fields Medal just working on the notes and extensions of Ramanujan. Then on 26 April 1920, at a very young age of 32, Ramanujan died. It was said that he was suffering from different problems like tuberculosis, severe vitamin deficiency, liver cancer, and even lead poisoning. So there are two very important books on Ramanujan. One is The Man Who Knew Infinity. Now, there's a movie also by the same name. And another is David Leavitt. The book is named The Indian Clerk, because as we know, Ramanujan was initially a clerk at Port Trust. So the book is about Ramanujan, so it is titled as The Indian Clerk. Then in 1962, on the 75th birth anniversary, the government of India issued a postage stamp in honor of this mathematical genius. And in 2011, the government of India decided to celebrate 22nd December, Ramanujan's birthday, as a National Mathematics Day in recognition of his contribution to mathematics. And since 2011, we have been celebrating this day as the National Mathematics Day. Initially, we used to celebrate it as the Ramanujan Day as Ramanujan Day, but now we call it to be the National Mathematics Day. And today, 22nd December 2021, which is the 134th birth anniversary, we pay respect and homage to this great mathematical genius, Srinivas Ramanujan. So this was a small presentation on Ramanujan, and now I'm going to move to the main topic of deliberation today, that is the foundation of mathematics. So the topic of today's deliberation is foundation of mathematics. It's a very broad area, so I'm just talking about some. I'm just going to give some glimpses.
Yeah.
Okay. So this is the overview of what we are going to discuss. What is mathematics? In other words, what is the nature of mathematics? And what are mathematical objects? Do they exist? Is mathematics discovered or invented? What are mathematical truths? And how do you find them? Then how certain is mathematics? Do mathematical propositions represent absolute truths? And finally, we'll end with what is called the beauty in mathematics. So start with the feel-good factor. All of us know that small minds discuss people, average minds discuss events, great minds discuss ideas, and I add, really great minds discuss mathematics. So some more quotations. So one given by Janet Van Erlicher, who was the Indian astrophysicist, who said, mathematics is a game functioning with a set of ground rules and governed by logic. Just as we have different games like football, cricket, chess, bridge, etc., each with its own set of rules or logic, so does mathematics have different branches: arithmetic, algebra, geometry. This is given by German mathematician C.F. Gauss, who said, mathematics is the queen of science and arithmetic is the queen of mathematics. Another American mathematician, John Newman, he said, if people do not believe that mathematics is simple, it is only because they do not realize how complicated life is. So compared to the complexity of a life, mathematics is actually very simple. Then another one by Nobel laureate and mathematician Frank Wilczek. He said, I went off to college planning to major in mathematics or philosophy. Of course, both these ideas are really the same. So he's just equating mathematics with philosophy. So mathematics has a lot to do with philosophy and vice versa. So you want to emphasize that mathematics is actually philosophy. A philosophy is mathematics. As you know, mathematics begins with numbers because that we as children were taught the numbers at a school. When you introduce to mathematics means we are introduced to numbers. And one mathematician, German mathematician, Kronecker, he said, God made the natural numbers. So natural numbers are the numbers that we are taught at a school at the very beginning. And the rest is the creation of man. So whatever we study afterwards, they are actually created by humankind. So God made the natural numbers. So we are talking about numbers. So we have the set of natural numbers. Now we are taught about the set of natural numbers or counting numbers. Now one mathematician, Piano, Italian mathematician, what he did, he gave 5 axioms, 5 statements. These are the 5 statements. So he actually defined the set of natural numbers or the set of natural numbers by these simply 5 statements, which are called axioms. The first says that there's an element 1 in n, where n is a set. And for each n, there's a unique element n dash called a successor. So for every small n, there is a successor n dash. And third condition is that if m and n are 2 elements in the set, then their successors are equal, then actually m and n are equal. And 1, that is number 1, is not the successor of any element of n. Then one more, that is if m is a subset of n and that m contains 1, n satisfies the condition that whenever n belongs to m, the successor also belongs to m, then this m becomes equal to n. So this last axiom is known as the principle of induction, and in mathematics we often use this principle of induction to prove different results. Now this simply from these 5 simple statements, which are called axioms in mathematics, what he did, he defined the whole set of natural numbers. whole set of natural numbers. And from this set of natural numbers, we can gradually construct the integers, the rational numbers, the irrational numbers, and finally the complex numbers. So natural numbers are given by God, and the rest are created by us, by these 5 simple statements, or what are called the axioms. Similarly, the order structure of R, which is a set of real numbers, can be also deduced from these axioms. In fact, the whole algebraic as well as the topological structure of the set of real numbers R and a set of complex number C can be obtained starting from the axiom. So axiom is simply a set of statements assumed to be true from which we can deduce different things. And in this case, we have seen that Peano, he gave just 5 simple axioms, and from that we can deduce everything about real numbers and complex numbers. So this is called axiomatization. This is called axiomatization. Means from axioms, we can deduce the results of mathematics. And all those examples of axiomatization are, one is Aristotle's syllogistic and Euclid's geometry. So Aristotle, we know, is a Greek philosopher, and Euclid, we know, is a Greek mathematician, who is also known as the father of geometry. Now, we also heard about Euclid's Elements. Now, what is this Euclid's Elements? It is actually a collection of 13 books, where he gave 23 definitions, 5 common notions, and 5 axioms. And simply based on these 23 definitions, 5 common axioms, and 5 notions, he deduced all the results on geometry existing at that time. Actually, Euclid didn't develop or introduce new geometry. What he did was, all the geometry that was existing at the time, he arranged them, he formalized them as an axiomatized system by simply giving 23 definitions, 5 common notions, and 5 axioms, such that all the results of geometry that were existing at that time can be deduced from this. So what actually Peano did, he gave 5 axioms from which all the results of real numbers and complex numbers can be deduced. Similarly, what Euclid did, he gave 23 definitions, 5 common notions, and 5 axioms, and from that, all the results of geometry can be deduced. So there were total 13 books. In book 1 to book 4, he dealt with elementary geometry. Now, some of the definitions that Euclid used are these. For example, a point is that which has no part. A line is a breadthless length, and so on and so forth. You can see the definitions are very vague. You see, what is a point? A point is that which has no part, very vague. A line is a breadthless length. The straight line is a line which lies evenly with the points on the surface. So this is how he gave some definitions. And these are just 7 definitions I'm mentioning. He gave 23, and he gave 5 notions. 5 notions. That is, things equal to the same thing are equal. If equals are added to equals, the wholes are equal. If equals are subtracted from equals, the remainders are equal. Things that coincide with one another are equal. So all these things seem to be very, very trivial or very, very obvious. But actually, they need to be taken into consideration to deduce results of geometry. And finally, he gave the whole is greater than a part. So this statement I have marked as red because we are going to discuss this later. So one of the axioms that Euclid take was that the whole is greater than a part, and we'll try to check whether this is actually so true or not. So these are the 5 axioms. Then he also gave 5 common notions, and he gave 5 axioms. The 5 axioms says that given 2 points, there is one straight line that joins them. A straight line segment can be prolonged indefinitely. A circle can be constructed when a point from its center and a distance for its radius are given. All right angles are equal. And there is a 5th axiom, which says that given a line L and a point P not on the line, there exists a unique line passing through P and parallel to L. So these are the 5 axioms, and this last statement I have again marked it as red because we'll have to see whether this actually is so obvious or so true or not. It is called the parallel postulate. So Euclid, what he did, he just considered 23 definitions, 5 common axioms, and 5 common notions, and deduced all the results of geometry existing at the time. So this is one common axioms I have marked as red, and this is another I have marked red, and we are going to discuss these 2 axioms and common notions later. Now, in other books, out of the 13 books, in other books, it discuss various aspects like geometric algebra, number theory, and Platonic solids. So, number theory is not a part of geometry, but still he included number theory in his elements. And book 13 deals with construction of 5 Platonic solids. So, these are the 5 Platonic solids that discussed by Euclid. We can see a tetrahedron, cube, octahedron, dodecahedron, and isohedron. So these are called the 5 Platonic solids. Now what happened? Euclid gave 5 axioms, and the 5th was called the parallel postulate. Now the first 4 axioms appeared to be very obvious, so people were not having any difficulty accepting them. But the 5th postulate, people were doubting, so they tried to verify it, or they tried to see whether it can be deduced from the first 4 axioms. But they didn't succeed. That means the 5th postulate cannot be deduced from the first 4. Consider a new axiomatic systems where the last postulate was replaced by its negation. And this resulted in the development of 2 new geometries called the non-Euclidean geometries. So negation of Euclid's 5th postulate gave what is called elliptic geometry, developed by Cesare and Riemann, where they replaced the 5th postulate by a statement, and another geometry called the hyperbolic geometry, developed by Nicholas Lobachevsky and Jonas Bolai, where they replaced the parallel postulate by this one. So there are 2 negations of the parallel postulate of Euclid, and depending upon that, 2 new geometries develop. One is called the elliptic geometry, other is called the hyperbolic geometry. And it has been observed that the modern scientific theories seem to indicate that large-scale structure of the universe is non-Euclidean. Euclid's 5th postulate is no longer a self-evident truth. So initially it was thought that Euclidean geometry is the only geometry. So parallel postulate was accepted without any question. But later mathematicians tried to obtain different geometries considering the negation of the 5th postulate, and that gave rise to non-Euclidean geometry. And it has been observed recently that the large-scale structure of the universe is non-Euclidean. So non-Euclidean geometry is more successful if we study the modern scientific theories. So since initially it was thought that the Euclid geometry is the only geometry and all the axioms are self-evident truths, but later due to development of non-Euclidean geometry, what happens that put to rest the myth or the belief that geometry and in general mathematics represents absolute truth. So initially it was thought that mathematics represents absolute truth, but when there emerged along with Euclidean geometry, non-Euclidean geometry like elliptic geometry and hyperbolic geometry, then it broke the myth that geometry or mathematics represents absolute truth. Then David Hilbert, another mathematician, what he did, he wrote a book, Foundation of Geometry, and he gave a complete examination of Euclid geometry by filling in the gaps of Euclid. Actually, what happens, the geometry of Euclid, there were certain gaps. So this David Hilbert, what he did, he filled up the gaps and he constructed a new kind of axiomatization of geometry. For Euclid, axioms are self-evident truths about geometry that were based on experience with physical space. But for Hilbert, so Hilbert actually didn't consider this geometry has anything to do with the physical space. He considered them as purely abstract concept. Okay, he simply deduced the results without taking into consideration the physical meaning or interpretation of the axioms. Well, Euclid thought that the axioms has got physical meaning, and accordingly he tried to develop his geometry. But Hilbert, what he did, he took a different approach and he started to deduce results from the axioms without considering whether those results or axioms has anything to do with the physical world or not. Okay, then come to the common notion I have told that Euclid gave this notion that the whole is greater than the part. Let us check whether it is true or false. Now we know that a set of natural numbers is a proper subset of the set of integers. So if I say the set of integers is a whole, then n is a part. But can you say z is greater than n? Similarly, the set of integers z is a proper subset of the set of rational numbers. The set of rational numbers contains the set of integers. But can you say the set of rational numbers is greater than the part z? Similarly, the set of irrational numbers qc is a proper subset of the set of real numbers. So can you say that a set of real numbers is greater than q complement? That is the question posed by many mathematicians. Now for that, we have to understand how we actually measure or talk about whether two sets are equal or whether one is bigger than the other. If we have, say, finite sets, if I have two finite sets, I can easily count the number of elements in both the sets and I can say which is bigger, which is smaller. But the thing is that if the two sets are having is infinite, then it becomes very difficult to say which is greater, which is smaller. So there is a process to compare two sets, and that is called a bisection. That is a 1-to-1 mapping from one set to another. Okay, so what is observed is that if there is a bisection from a set to a proper subset of itself, then the set is infinite. In fact, this is the very characterization of an infinite set. So infinite set is defined sometimes like this, that a set is infinite if there is a bisection from X to a proper subset of itself. So as we'll see that we can see here what is called a cardinality of set. The cardinality of set. So we talk about size of the set. So how we compare, if the two sets are finite, we can simply count the number of elements and say they are equal or they're not equal. But otherwise, what we do, we try to define a bisection from the two sets. If the bisection between the two sets, then we say that two sets are equivalent. That means they are of the same size. So if X and Y equivalent, there's a bisection from X to Y. Now, if we consider the set of integers Z and a set of natural numbers, then Z actually contains N, but still we can have a bisection from Z to N. By this one, 0 goes to 1, natural number 1 goes to integer 2, integer minus 1 goes to natural number 3, 2 goes to 4, minus 2 goes to 5. In this way, we can continue the process. So we can define a bisection from Z to N. And whenever there's a bisection between two sets, we say they are equivalent, or we say they have the same cardinality. That means they have the same size. That means they are equal. Neither is greater than the other. So from this, we can say that though N is proper subset of Z, N is not smaller than Z. In other words, we can say that N is a part of Z. Z is a whole, N is a part. But still, the whole is not greater than the part. Because as you can see here, there's a bisection between Z and N. That means the set N and the set Z, they are equivalent. Neither is greater or smaller than the other. So the basic notion that Euclid considered that the whole is greater than the part is actually not true. Not true. So one basic common notion that Euclid considered in his book, that the whole is greater than the part, comes out to be not true. It is false actually. Then we come to the idea of mathematical objects. Now, what do you mean by mathematical objects, and whether mathematical objects exist in real life or not? So as we know, point, line, set, these are called the mathematical objects. But what is the point? Euclid defined a point as that which has no part. What is the line? Again, he defined that line is breadthless length. But can you find a line or a point in nature reality? So if I put a dot on a piece of paper, I may say it is a point, but if I magnify it, then it will appear as a disk. So it is no longer a point. Similarly, if I draw a line on a piece of paper, and if I magnify it, then it will appear as a strip. So it is not a line, because by definition, a line is breadthless, because if I magnify it, then that line will appear to be having some breadth. Similarly, a point will have a part, because the point, a dot on a piece of paper, when magnified, will appear as a disk. So in reality, actually, it is not always possible to find the mathematical objects, though we talk about points and lines very easily. Similarly, number is also an object, but can we find a number? For example, number 3. Can one give me the number 3? Of course, one can give me 3 apples or 3 books, something like that, but none can give me the number 3. So number 3 is a mathematical object, but whether it exists or not. So the question comes, do mathematical objects exist? So actually there are not disagreement among mathematicians, and there are 3 views on this issue. Some say that all the mathematical objects exist. Others say that no, some of the mathematical objects exist, may not all exist, but some of them exist. But a third view is that none of the mathematical objects that we discuss exist. So we have 3 philosophies. The first is called a Logicist, developed by British mathematicians Barton Russell and A.N. Whitehead. Now, this school, they believe that there is a Platonic world, there's abstract world in where all the mathematical objects exist. May not be here, but there is a world where beyond our, say, perception, where the objects exist. They feel that there's external world or eternal world beyond our perception where the mathematical objects exist. This is the first view, called the Logicist. The second school of thought is called the Intuitionist. It was developed by Dutch mathematician Brouwer. And this Brouwer, he made the comment that God made the whole numbers or natural numbers and rest the work of man. So for this school, they believe that only the whole numbers exist and the rest are actually created by man. So for them, some mathematical objects exist, but not all. Then there's a third category of mathematicians. They are called a formalist. They were developed by the German mathematician David Hilbert. And according to David Hilbert, no mathematical objects exist because he feels that mathematics is nothing more than a game played according to certain simple rules with meaningless marks on the paper. The game is to deduce theorems from axioms. Axioms need not refer to any reality. So he's completely away from the real world. So he says that no, mathematical objects do not exist. We simply assume them. And this mathematics is simply a game that we are playing or we are doing with some meaningless marks, because the axioms that we treat or consider need not refer to reality. If someone wants, they can give some physical meaning, but otherwise there is no need to give any physical meaning. So they are simply abstract ideas or concepts. So it brings us to the question whether the mathematics that we discuss or that mathematics that developed by different mathematicians, whether it was discovered or invented, whether a result is discovered or result is invented. Now, according to the 3 different schools, they have different views. The logicist says that mathematics is discovered because the logicists believe that there is an eternal world, but there is a Platonic world where all the mathematical objects exist. All the results are there. Only we human beings simply discover the results, existing results. Where the other 2 categories, the intuitionist and the formalist, they feel that no, mathematics is not discovered. Actually, mathematics is created by man. So next come to the question of what are mathematical truths. Mathematical truths. So suppose one mathematical statement is given. So what do you mean by the mathematical statement is true? Or how can you judge the mathematical statement is true or not? What does it mean for a mathematical statement to be true? Now, Aristotle said that truth of a statement consists in its reality, in its agreement with reality. So if a statement is given, we can check whether the statement is true. What you have to do, you have to simply compare the statement with reality. If it agrees with reality, then we can say, yes, the statement is true. If it is not agreement, if it is not in agreement with reality, we will say the statement is not true. However, there's a problem because there's a reality. It is not clear in case of mathematics or even in case of science that there's a reality against which a mathematical statement can be compared. And we will see that there are mathematical statements which we cannot actually judge to be true or false because it is not possible to compare the statement with some existing reality, as Aristotle said. So, as I told you that there is disagreement among mathematicians on different issues. So in case of mathematical truth, though Aristotle said that truth of a statement consists in its agreement to reality, but as I have told you that it is not always possible to compare a statement with some existing reality. So there's a problem. But we need some definition of mathematical truth. So the mathematician thought that this should be the operational definition of mathematical truth. So a statement or mathematical statement will be considered to be true if it can be deduced from something that is known to be true. And to deduce, they must use some principle of argumentation. Now, this is the definition of mathematical truth that Euclid used. Okay, so the mathematical truth, a statement will be true if that statement can be deduced. It may not be possible to compare with some reality, but if we can deduce it from some already known statements by some commonly accepted logic or argumentation, then that will be a true mathematical statement. However, mathematicians still differ regarding the commonly accepted principle of argumentation and already known to be true. Because if we want to deduce some results, we have to assume some result. So all mathematicians do not agree what is known to be true. And moreover, the method of obtaining the results, all mathematicians do not agree. The commonly accepted principle of argumentation and already known to be true, these things are not accepted equally by all the mathematicians. Some mathematicians may have some reservation regarding one statement to be accepted to be true. Another may be having reservation regarding the logic of deduction. So there's a great problem. For example, I'll give you one example where there is disagreement among mathematicians regarding the principle of argumentation. As we know, there is a very famous or very familiar or usual method of proving a theorem, and that is called the method by the contradiction. Method by contradiction. If we want to prove a statement, we take the positive and then we come across a contradiction. Then we can then say, since you're coming across a contradiction, so the original statement must be true. So this is called a proof by contradiction. But Brouwer, the mathematician Brouwer, who believes in the school called the Intuitionist, he doubted that any non-constructive existential proof. He will not accept the principle of argumentation given by the proof by contradiction. So I'll give an example here. So this is an example of a result which is not accepted by Brouwer because he doesn't believe in the method by contradiction, and this is what Russell and Whitehead, the founder of the Logicist school, they will agree. So let me discuss this example. So as you know, pi has a decimal expansion. So it's a very long expansion, never ending. So the question is coming that the pi, the expansion may or may not contain the consecutive digits 1, 2, 3, 4, 5, 6, 7, 8, 9. So these consecutive digits may not appear consecutively in the expansion of pi. We don't know. So let us say that k denotes the number of decimal digits of pi before this sequence of numbers. It may or may not appear. So if it never appears, we will put the value 0 for k. So if it appears, then it will be either even or odd. So k will be either even or an odd counting number or 0. So we can then think of a number p, which is -1 to the power k. So p equal to -1 to the power k. But what is k? K will be 0 if that sequence doesn't appear, and if it will be then okay. If the number it is either even or odd. Okay. So what happens? Brouwer will not accept the existence of the number p because we cannot exactly find out the value of k. We can just assume that k will be 0 or k will be even number or k will be odd number. But since we cannot exactly find out the number k, so Brouwer will not accept the existence of the number p, because we cannot obtain the number k by a finite number of steps. Because this expansion of pi is an infinite expansion, so we'll never be able to find a value of k. Since we cannot find the value of k, so p, which is equal to -1 over k, will not exist for the Brouwer. Whereas Russell and Whitehead will have no problem in accepting the existence of this number. So this is one method where the mathematicians disagree. Similarly, there are some axioms also where mathematicians disagree. So this is one from set theory. So consider the following case. Say, given two non-empty sets, any two non-empty sets, we can always construct a set containing exactly one element from each set. Suppose one set is A, another set is B. We can take an element from A, we can take an element from B, and we can construct a new set having the two elements. Now, if we are given three sets, same thing we can do. Suppose set A, B, C, we can take an element from A, we can take an element from B, we can take an element from C, and we can form a new set having three elements. So for any finite number of sets, this can be done. But the question is, what happens if instead of finite number of sets, we take infinite number of sets? If we consider infinite collection of sets, whether the same construction can be done or repeated. For a finite case, it is no problem, but for infinite case, whether it is possible or not, we cannot say. So some mathematicians, they accept that it can be done. And that is called an axiom. It says that given a non-empty family X alpha of non-empty sets, there exists a set A which has exactly one element from each X alpha. So collection X alpha is infinite. So this axiom says that yes, it can be done. If we are having a infinite family of sets X alpha, then it is possible to construct a new set which will consist one element from each X alpha. So this is called the axiom of choice. And this axiom of choice is used. This is usually used in standard axioms of set theory. But there are mathematicians who refuse to accept its validity. And there are some other variants of this axiom, sometimes called a John's lemma or well-ordering principle. And this axiom of choice is used in many proofs. For example, to cite Tychonome's product theorem is there on compactness. Then we have a result, very familiar result, every vector space is a basis. So in this type of results, we use the axiom of choice to be true. Okay, but we also don't know whether the axiom is true or not, because we cannot establish its validity or truthiness. Now, the validity of all those results is directly dependent on the validity of the axiom of choice. So since we use the axiom of choice to prove that every vector space is a basis, so that every vector space is a basis is true, provided the axiom of choice is true. But we have no way of examining whether the axiom of choice is true or not. But still we work with it. So what you have seen is that there is disagreement among the three schools of thought on the existence of mathematical objects, then what is mathematical truth, whether mathematics is discovered or invented, and there is disagreement among the axioms. Some may accept an axiom, other mathematicians may not accept, and there is also disagreement among the logic of deducing results from known results. So these are some of the disagreement that we find in case of mathematics. So the question comes, how certain is mathematics? How certain is mathematics? And as we know, this is a saying by quotation by Albert Einstein, as far as the laws of mathematics refer to reality, they are certain. As far as they are certain, they do not refer to reality. So this expresses the uncertainty of mathematics compared to the real life. So we have the problem of uncertainty in mathematics. Now, one Austrian mathematician, K. Gödel, he established that mathematical certainty cannot be achieved through deductive method, even if everyone were to agree on a common list of axioms and rules of logic. So initially we are having the problem that there was disagreement among the mathematicians regarding the accepted principles of argumentation and statements already known to be true. That means there was a disagreement among mathematicians regarding the axioms and the method of deduction. But Gödel said that even if the mathematicians agree on these two issues, still we cannot have mathematical certainty. There will be still uncertainty exists in mathematics. So for that, we need to understand two things. One is called consistency, another is called completeness. A consistency means what? Suppose we are having an axiomatic system. It means we are having some axioms. The axioms are consistent means the results deduced from the axioms should not contradict one. They are consistent. That means no contradictory results can be derived from the axioms. For example, we have the Peano's axioms. So Peano's axioms will give a lot of results. So results should not contradict. If they contradict, we will say the axioms are not consistent. Similarly, Euclid gave some axioms from which we deduce geometry, different results of geometry. And if there's a contradictory result, we will say the axioms are not consistent. So the consistency is that the results deduced from axioms should not contradict one another. So that is our consistency. Then completeness. Completeness means what? Any valid mathematical statement must be deducible from the axioms. That means if I give any mathematical statement of geometry, it must be deduced from the axioms that I have taken. Similarly, if I consider one statement of number theory, it must be deducible from the axioms of number theory. So this is the completeness. That means every valid mathematical statement must be deducible from the axioms. So whenever we have an axiomatic system, it must be consistent. That means there should not be any contradictory results, and it must be complete. That means all the mathematical results must be deducible from the axioms. But what we have seen is that we have two incompetence theorems. The first incompetence theorem says that in axiomatic system, there are valid mathematical statements that cannot be proved within the system. That means we cannot guarantee that our axiomatic system will be complete. We cannot say with certainty that all the mathematical results can be deduced from the system. So this is the first one. An example of this is the continuum hypothesis. As we know, I've talked about the cardinality of set, and the set of natural numbers and the set of real numbers, both are infinite set. And the set of natural numbers is assigned a cardinality called aleph naught, and the set of real numbers is assigned a cardinality called C, the continuum. Okay, and it can be verified or shown that this cardinality of R is greater than the cardinality of N. Now, the question is that whether there is a set which our cardinality lies between N and R, whether there is a set whose cardinality lies between N and C. So the answer is yes as well as no. The answer is yes as well as no. Now, mathematicians, they have not been able to find any set whose cardinality lies between aleph naught and C. That means they have not been able to find a set whose cardinality lies between the cardinality of N and the cardinality of C. But that doesn't mean that there doesn't exist. We have not been able to find only, but still, since they couldn't find, so they assume or they took this hypothesis that there exists no set whose cardinality lies between aleph naught and C. Nobody has verified this fact, but simply since they have not been able to find such a set, they assume or call it a hypothesis that there exists no set whose cardinality lies between aleph naught and C. Now, what German mathematician Cantor did and Gödel, they tried to establish this hypothesis, but they couldn't. So what Gödel did, he took this approach. Already some axioms of set theory are there. He included the continuum hypothesis to that collection of axioms. And what is found that there is no contradiction. So it appears as if the continuum hypothesis is true because it is not contradictory to the existing axioms of set theory. So we can say the continuum hypothesis is consistent with the axioms of set theory. So it appears that the continuum hypothesis is true. But what happened? American mathematician Paul Cohen, what he did, he assumed the negation of continuum hypothesis. That means there exists a set whose cardinality lies between R and N. Okay, and he assumed the negation, and he still found that that statement is also not contradictory to the standard axiom set theory. So we are having a very difficult situation. Thus, Gödel and Cohen has shown that mathematics could not use their commonly accepted notions to determine whether a continuum hypothesis is true or false. So we cannot establish that a continuum hypothesis is true or it is false. If we assume it is true, we don't get a contradiction. If we assume it is false, then also we don't get a contradiction. So as a consequence of this, mathematicians were led to a very disappointing conclusion. And that is that there can be two types of mathematics. One where the continuum hypothesis is true, and another where the continuum hypothesis is false. Then a second incompetence theorem, which says that the axiomatic system must be consistent. But there's again a problem. The second incompetence theorem says that the consistency of an axiomatic system could not be proved within the system. Now Hilbert, he tried to prove the consistency of the list of axioms of Euclid. So Euclid gave some axioms and Hilbert tried to establish the consistency, but he couldn't. Then in Descartes, using Descartes' coordinate geometry, Hilbert established that if the axioms of arithmetic are consistent, then his axioms for Euclid geometry are consistent. He directly couldn't prove that the axioms of geometry are consistent, but he showed that if the axioms of arithmetic are consistent, then of course his axioms are consistent. However, Gödel, in his paper on formally undecidable propositions in Principia Mathematica and related systems, established that the axioms of arithmetic are consistent can neither be proved nor disproved unless one works in the larger system. So Hilbert said that if the axioms of arithmetic are consistent, then Euclid's axioms are consistent. But Gödel proved that the axioms of arithmetic cannot be proved to be consistent or inconsistent. So these two incompetence theorems forever undermine mathematical uncertainty. So we have seen that though apparently it appears that in mathematics everything is very precise, everything is very absolutely true, there is no contradiction, no disagreement, but that is not a fact. If we go into deep in the philosophy of mathematics, we see there is a lot of contradictions, lots of disagreement, lot of uncertainty in mathematics. So to take some relief from this uncertainty of mathematics, let us move to what is called the beauty and aesthetics of mathematics. The beauty and aesthetics of mathematics. So mathematics is not just about numbers, formulas, and the language of mathematics is a convenient tool for comprehending and communicating these underlying structures. Pythagoras said, where harmony is, there are numbers. So as you can study nature using mathematics, similarly, we can study music using mathematics, because the language of mathematics can be conveniently used to study music. Pythagoras is considered to be the first music theorist. Why? Because by observing the sound of hammering of blacksmiths, he discovered that two hammers would produce harmonious sounds only when the ratio of the weights equal a ratio of two whole numbers. So this observation was made by Pythagoras by hearing the sound of hammering of blacksmiths. And he established the relation of mathematical ratios and musical harmonies. So he was the first person to establish or see a relationship between music and mathematics. So he is termed to be the first music theorist. And we can see a lot of interplay of mathematics and music. As you know, musical notations such as octaves, chords, bits, tempo, time signature, measure, scales, keys, lots of other things are there. They can be made understandable using logical, simple mathematics. A music interval, as you know, is the ratio of the frequency of the sound wave of two tones. If the second tone has pitch double that of the first, then we get an octave. And a music scale is an ordered sequence of notes in an octave. Scales are considered building blocks of music composition, and its creation is essentially an arithmetic process. The chromatic scale, which consists of 12 notes within an octave, can be modeled by the group of integers modulo 12. In algebra, we have this concept. In ring theory, on algebra, we have this concept of group of integers modulo 2. And the chromatic scale actually consists of 12 notes. It can be modeled by the group of integers. Similarly, diatonic scale consisting of 7 notes can be represented by Z7, group of integers modulo 7. And we know a chord is a triad or quadruplet from Z7 or Z12. So this is a relation between mathematics and music. And it is interesting to note that from a single chord, by applying some transformation in inverse functions on Z12, all the other chords can be obtained. So even coordinate geometry and graph also find their place in music. The staff notations in music, as you know, music can be written in staff notations with symbols. So they are similar to mathematical graphs of discrete function in two-dimensional Cartesian coordinates, where the nodes represents the coordinates. So the staff notation actually represents a graph for the music. Even mathematical terms like harmonic series, harmonic analysis originate from the term harmony of music. So the harmonic terms is first came from music, and then we have taken it in mathematics like harmonic series and harmonic analysis. So are we living in a mathematical world? Perhaps the ultimate interplay of mathematics and music comes to the fore in string theory. And string theory, as you know, is the most modern mathematical model to explain the universe. According to this theory, all objects in our universe are actually composed of tiny vibrating string. Each type of vibration corresponds to a different particle. The different particles are like different notes that are played on guitar or violin string. Thus, music is not only inseparable from the universe, it in fact determines the structure of matter. In other words, music depicts, or rather we can say dictates nature. So this is the ultimate relationship between mathematics and music. So the question is, are we living in a mathematical world? Now, mathematician, a theoretical physicist, Paul Dirac said, it is more important to have beauty in one's equation than they have with experiments. So he is giving importance on the beauty of the equation rather than being applied to an experiment. And G.H. Hardy, the person who actually invited Ramanujan to Cambridge, G.H. Hardy, he remarked, a mathematician like a painter or a poet is a maker of patterns. The mathematician's patterns, like the painters or the poets, must be beautiful. The ideas, like the colors of the walls or the walls, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. So he's talking about ugly mathematics. You can see Paul Dirac also emphasized that beauty is more important than fitting in an experiment. Similarly, Hardy is saying that beauty is the first test for a result. Ugly mathematics has no place. And we know mathematicians are not satisfied with single proof. They venture different, beautiful and elegant way of proving the same result. For example, we all are familiar with the Pythagoras theorem. It has got 350 proofs. One proof is sufficient, but why 350 proofs? Because mathematicians, they are not satisfied with a single proof. They try to prove the same thing in different, beautiful and elegant way. Similarly, there is a theory called the theorem of quadratic reciprocity in number theory. It has got 150 proofs, and out of which 8 were given by mathematician Gauss himself. And we have here a very beautiful mathematical formula, e to the power I pi plus 1 equal to 0, which connects the 5 fundamental mathematical entities, 0, 1, I, root over minus 1, pi, the ratio of circumference by diameter, and e, which is the limit of 1 plus 1 by n to the power n as n tends to infinity. And this e is the base of Napierian logarithm. So these 5 fundamental mathematical entities are connected by a single formula. So it is a very, very beautiful formula, we can say. Then as regard beauty, we have what is called a golden ratio and Fibonacci sequence. Golden ratio is a ratio of 2 lengths such that A by B is A plus B by A. So if 2 lengths satisfy this condition, then that ratio is called a golden ratio. And the value of this ratio is approximately 1.6. And we have what is called a golden rectangle. So if we consider rectangle and if we take the ratio of length by breadth, if it comes out to be golden ratio, then we call it golden rectangle. And if we consider different rectangles, the golden rectangles will be appearing to be most visually pleasing. Most visually pleasing. Similarly, we have golden triangles. We can consider isosceles triangles. Isosceles triangles mean two sides are equal. Now, if an isosceles triangle is such that the ratio of one of the equal sides to its base is a golden ratio, we call it to be golden triangle. Now, if we consider many triangles, out of many isosceles triangles, out of those isosceles triangles which are golden triangle, they will be appearing to be most visually pleasing. So here we can see this is a rectangle. This is in the golden ratio. Length by breadth is golden ratio. Then what happens? One square is removed. What is left? Blank again is a golden ratio. Then from this blank again another square is removed. What is left? The golden ratio. So in this process, we can continue the process. Okay. Each time we subtract a square from the golden rectangle, and what we get is again a golden rectangle. And what happens? Now, so these are the golden rectangles. Now, if we start from here and make a curve touching all these rectangles, what we obtain is a figure like this, the snail. So it's called the golden spiral. Golden spiral, and we always we see this structure in nature. So this golden ratio is also present or prevalent in our nature. Then in pyramids we can see. The pyramid, what they have done, they have taken the base length of pyramids to the height appears in golden ratio. That is why these pyramids looked very beautiful. And in our body, we can see the length of these bones of our fingers and hands, they are in golden ratio. They are in golden ratio. And this is again a golden ratio. This is again a golden rectangle. So this type of golden ratio or golden rectangles, they appear frequently in nature and in our human structure. For example, we can see here many golden rectangles appear here. For example, the ratio of the face, length of the face over wideness of the face, length between the lips and eyebrows over length of the nose. So in this way, by considering different parts of the body, always we find they approximately equals the golden ratio. And more closer the ratio, the more beautiful that person appears. So then this is a bird, you can see here. So this length is to this length is again in golden ratio. So I'm coming to the end. Few more slides are left. So then this now Fibonacci sequence. Fibonacci sequence is a sequence of numbers. This is called a Fibonacci sequence, where any number can be obtained from the previous one by adding the two, excluding the first term, of course. So these two can be obtained as 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 8. So in this way, you can continue. And that sequence is called a Fibonacci sequence. And that Fibonacci sequence also appears in nature. For example, one example I'm giving here, this growth of this tree, branching of this tree is in the satisfies the Fibonacci sequence. 1, then 2, then 3, then 4, then 5, and this should be actually 8. Sorry, 5 plus 8, it should be 9. Sorry, 8, it should be 8. This is a 1, 2, 3, then this should be 5, this should be 8. Okay, this should be 8. So in this way, how the tree grows, satisfying the Fibonacci sequence. Fibonacci sequence also, as in case of golden ratio, similarly Fibonacci sequence also occurs or appears in the bones of our hand, as you can see here. The lengths are approximately 2, then 3, then 5, then 8, and so on and so forth. So we can see that Fibonacci sequence also makes appearance in a human body. Then even in music, mathematical objects like Fibonacci sequence and golden ratio, as I mentioned, are observed in music also. The climax of a song, for example, is often found at that point of golden ratio. That is approximately 61.8% of the way through the composition. For example, a 32-bar song would have its climax at bar 20. Studies have shown that Mozart used golden ratio in his work. Use of golden ratio is also seen in design of different musical instruments. Already we have seen violin. The analysis of the works of Beethoven, French composer Claude Debussy, and other musical innovators in different musical periods shows the presence of Fibonacci sequence. So in conclusion, what we have seen is that there is uncertainty in mathematics, but there's also beauty in mathematics. And as emphasized by the Nobel laureate Paul Wigner, there is unreasonable effectiveness of mathematics in the natural sciences. So we have uncertainty, no doubt, but we don't have problem because we have effectiveness or unreasonable effectiveness of mathematics in natural sciences, because mathematics, as you know, is applied to each and every branch. And there is also something to enjoy because there is beauty in mathematics. So what is important is not whether mathematics represents truth or reality, but that it works and gives us pleasure. It is only the limitations of our imagination that can constrain the utility, applicability, and fate of mathematical objects, concepts, and theories. So only because of our limitation, we may not be able to apply the mathematics, or we may not be able to enjoy the mathematics. It is only the limitations. So with this, I'd like to conclude my presentation. Thank you for your patience. Thank you, everybody.
Thank you, sir. Thank you very much. It was indeed a very robust explanation of the foundations of mathematics.
Yes,
So you have touched on almost, I must say, all the foundations possible. And thanks for the introduction and of Ramanujan and his life, because many of us, or some of us rather, may not have paid attention to his struggle,
yeah,
as he was the greatest mathematical genius of our own country, and he impacted the global mathematicians
yeah.
around. Yeah. So thank you on that note, and thank you for this very much enlightening terms in mathematics that you've shared with us. Yes, thank you very much, participants, because we all were the main people who have graced this occasion today. So take care and goodbye. God bless. Be safe. Thank you, Professor.
Thank you all.
Yes, thank you so much. Yeah.